So when we look at a long bone, we name the regions of the long bone, and long bones are easier to understand than the other types of bones, irregular bones, etc. Uh, but it all ends up working about the same way. So we'll stick with the long bone because it's the most straightforward. So when we look at a long bone, the shaft of the long bone is called the diaphysis, which means between uh, the active part, the physis. Uh, so uh, they are not. It's not a simple shaft. They, what it is a collar of bone surrounding a cavity, and we call it the cavity in the middle, the medullary cavity, or sometimes called the marrow cavity. And you've all seen it, like if you've seen a ham, that bone is hollow. It's a compact ivory bone with a hollowness in the center, and they tend to in the grocery store sell them as soup bones because the the cavity is filled with yellow marrow, which is mostly fat. It's rich, and it makes good soup. So that's why they tend to sell them as soup balls. Bones. It's the bones that dogs like because they're trying to get at that marrow and get at the proteins that are there. Um, the ends of the long bone are called the epiphysis, above the the uh, the plate. So they tend to be expanded on the ends. Their interior isn't hollow per se, but more spongy. It's like sponge toffee. It's spongy bone. Um, and in adults, there's a line between the epiphysis and the diaphysis called the epiphyseal plate. In uh, in children, this epiphyseal line is called the epiphyseal plate or the growth plate, and it's made out of cartilage, and it allows the bone to grow longer. Um, at the ends of the bones, there's articular cartilage, so it ends up looking like this, with a medullary cavity filled with yellow marrow, spongy bone at the ends, the epiphyseal line, articular cartilage. Um, in the spongy bone, these are the trabeculi, and this is where we get the red marrow. This is where bone or blood cells are formed. The whole thing is surrounded by kind of a collar of compact bone uh, to give it rigidity. The the bone is surrounded by uh, some connective tissue. Bone itself is connective tissue, but it's surrounded by another layer of connective tissue proper called the periosteum. The outside layer of the periosteum is fibrous. That's a dense, irregular connective tissue. And again, you may have seen it, especially if chicken or turkey or something is overcooked. It comes off the bone as a sheet almost. But in living bone and bone that has not been subject to high heat, the the periosteum is very firmly attached um, to the bone itself. The inside layer of the periosteum is called the osteogenic layer, and this is where new bone is made. New bone is made by bone forming cells called osteoblasts. Old bone is taken away to be replaced, so it's kind of like a remodeling or a maintenance. It's taken away by osteoclasts, and it's maintained by these osteoblasts and um, and we're going to see later osteocytes come from stem cells, osteogenic cells. This layer of periosteum has the nerves, the blood vessels, lymphatic vessels, and all of that kind of stuff in it. This is the part that where the nerves, when you fracture a bone, this is where the pain happens, because this is where the nerve endings are. excuse me, when kids are having growing pains, what's happening is that the bone is growing faster than the periosteum, and those nerves get stretched, and that's what gives that deep, achy pain that kids experience. So all of this is made out of collagen fibers, and we'll see in a minute that the bone primarily is made out of collagen fibers, and the collagen fibers that kind of bridge the gap between the collagen of periosteum and the collagen of the osteoid are called Sharpie's fibers, probably named after Dr. Sharpie. The medullary cavity is also lined by a membrane, and it's called endosteum, as opposed to the periosteum, which is around. The endosteum is very similar. It's a little more delicate. It's not as robust, but it has osteoblasts and osteoclasts in it. So there's remodeling happening at that layer as well. So that it ends up looking kind of like this. The Sharpie's fibers are kind of anchored in the bone and anchored in the periosteum. The endosteum lines the medullary cavity. Bone is very highly vascular, so the arteries, the nutrient arteries, pass through the periosteum and they pass into the bone itself through little holes called nutrient foramen. The rest of the bones are periosteum covered, compact on the outside. The endosteum covers the spongy bone inside. That's where in the spongy bone, that's where the trabecular are found, and red bone marrow is found in there. It kind of looks, well, there's a photograph of it. It looks exactly like that. So that space, all the space left in the sponge, is filled with red bone marrow. And red bone marrow is where we make blood cells, which is called hematopoietic tissue or hemopoietic. Either one is the British name, the other one's the American name. So it happens in between the trabecula, and each trabecula, by the way, is covered with an endosteum. So it seems to be more concentrated in the proximal end of the femur and the humerus, in the flat bones, so in the pelvis, in the skull, in the scapula, in the ribs, that kind of thing. So that's where we find it. So I started to mention the cells. So osteogenic cells are stem cells. They give rise to the osteoblasts and ultimately the osteocytes. Another type of cell, and a very important type of cell, is an osteoblast, and they form bone. They really are a lot like a fibroblast, because what they do, they form the fibrous part, the organic part of bone, the osteoid, so which is basically collagen fibers. The mineral salts that harden bone are deposited later. They're not deposited by the osteoblasts. So they look like this. The biggest difference you can see here is that there is way more endoplasmic reticulum and Golgi apparatus in it, and there's more surface area because it makes collagen proteins and secretes it. Osteocytes are the mature bone cells. They maintain the bone cells, and osteoclasts remove and reabsorb bone cells. And it does it to remodel bone, to take away old, kind of damaged bone tissue so that it can be replaced with fresh new tissue. A real good analogy, as to the importance of osteoclasts is what's happening right now on the Gardiner Expressway in Toronto. The Gardiner Expressway is made of reinforced concrete. There's steel rebar covered in concrete. But there's moisture has gotten in and the steel rebar is rusted. And so now big chunks of concrete fall off and are landing on the roadway beneath on the lakeshore. It's it's becoming structurally unsafe. And the reason that it's happening is because 15 or 20 years ago, we had governments that were very fiscally responsible, meaning they didn't want to spend money on maintenance. What should have been happening all along is that cement, that reinforced cement, each one of those pillars should have been worked on a regular basis. And you often will see that when you're driving on the highway and the overhead bridges and things. What they do is they take away the concrete, get down to the rebar, they put new rebar in, and then they put new concrete over the top so that it's structurally sound. If the rebar inside the concrete is rusted, then there's nothing to protect against tension, and eventually big chunks will fall off. It's the exact same thing with bone. The rebar is osteoid, and the concrete is the bone salts. The bone salts need the osteoid in order to have structural integrity, and so it has to be removed and replaced on a regular basis. If the osteoclasts are working faster than the osteoblast, we end up with something called osteoporosis, and the bones, there's just not enough bone. One of the problems with some of the drugs for osteoporosis, things like Fosamax, is that what they do is they slow the osteoclastic activity. They don't speed up the osteoblastic activity. They slow osteoclastic activity. So what ends up happening is that people get more density in their bone because less bone is being removed, but it's poor quality bone. And oftentimes people get some very awful things happen because they'll get tumors of bone and things like that because this bad bone isn't removed. If you are so inclined, Google Fosamax jaw, and you'll be grossed out by some of the pictures of what people have with necrosis of their jaw. I'll talk about this in a couple of minutes when we talk about what causes bone growth, what causes osteoblastic activity and osteoclastic activity. It's called Wolff's Law. So it happens in the jaw because the jaw, in the act of chewing, gets more force than most other bones. So it happens usually there. So when we look at compact bone, what we're seeing is these tubes of bony cells, and it's arranged in layers like wood in a tree, and it works the same way. So these layers are called lamellae, which means layer, and they surround a blood vessel and a nerve that's in a central canal. We used to call it the Havasarian Canal. You'll still see that name now and then, but it's now more correctly called the Central Canal. And it kind of looks like this, with a central canal and layers of bone deposited around it, with the collagen fibers running in right angles to one another, so that it takes stress from a number of different directions. Each central canal is joined to other canals by perforating canals, which used to be called Volkmann's canals. And there's a blood vessel and a nerve, etc. there. Now, each of the osteocytes, the cells that maintain the bone, by the way, osteoblasts you can think of as construction workers. Osteocytes are more like maintenance people, like janitors. Osteoclasts are more destruction. They tear things down. So the osteocytes need to be nourished. And so they live in little lacunae, little spaces within the bone, and those spaces fill up with interstitial fluid, and the interstitial fluid carries the oxygen and nutrients, etc., takes away the waste products. But because bone, the mineral salts aren't very porous, there has to be little cracks that join the lacunae, little canals, as it were. And so they're called caniculi, which means little canals. So that it looks like this. Each central canal here, there's a perforating canal here, and each one of these little spots here is a lacunae, like this. And each of these little cracks coming off the lacunae are caniculae. And they just allow the flow of interstitial fluid through the bone. Spongy bone have got these structures called trabeculae. They're basically struts. And they align along lines of stress. And they're absolutely unique. They're as unique as fingerprints. Everybody has a different pattern of their trabeculae, enough that you can identify bodies. If you have an x-ray of the bone that you're examining, you can identify as surely as fingerprints by the direction of the trabeculae. And the lines of stress depend on what you do. So a baseball catcher's knees will have far different stress, and so therefore different trabecular patterns than somebody that doesn't squat like that. The street vendors in South Asia that squat on the sidewalks and selling and doing that will definitely have different hips and different knees trabecular pattern than people that don't do that. And I think that it's a little bit variable over life depending on what you do. I think that if you take up being a baseball catcher, your knees eventually will change. The trabecular pattern in the bone will actually grow to help alleviate the stresses placed on the bones because of that position. There's less patterning in the caniculi and the osteocytes and the lamellae, and there's no osteons. There's no central canal and things like that. So this is much more like open strut work. This is compact bone, and I don't know where well, trabecular bone will look like this. And all of these little trabeculae, and trabeculae means wall or strut, will align along stress. So what's bone made out of? It's connective tissue, so there's cells and there's matrix. The cells are osteoblasts, osteocytes, osteoclasts, and osteogenic cells. The fibers, it is an extracellular collagen fiber. It's called osteoid. It's organic. It's made of proteins. It's secreted by the osteoblasts. And the ground substance is there as well. So there's some glycoproteins and things like that. But this is the organic part of the bone. This is the stuff that the cells secrete. There's also a mineral component of bone, inorganic, and it's hydroxyapatite is the name of the salts. It's usually calcium phosphate, but there's other things in it. There's some magnesium, and there's various things, but it's mostly calcium phosphate crystals. If the bones that you handled in the lab, which were real bone, by the way, the real human bone, the reason that they were delicate and kind of fragile is because the organic parts of it has mostly rotted and deteriorated and isn't there, and all that was left is the hydroxyapatite, which makes the bones very brittle because they're not reinforced by the collagen. So what it is the analogy of reinforced concrete is apt here. This is the concrete, hydroxyapatite. The osteoid is the rebar.